Welcome and thank you for attending my talk. My name is Fёdor Picus and I'm a chief scientist, formerly of Mentor Graphics, now of Siemens Digital Software Division. And I'll be talking about branchless programming in C++. So before we talk about branchless programming, we're going to spend a fair bit of time explaining why branchless programming came up to attention of the C++ community. It's a performance-related issue, so we talk about performance, optimizations, understanding of how to use hardware efficiently, in particular, understanding of how conditional code impacts efficiency and how it's optimized. Okay, let's start with a kind of teaser for the presentation. So what can we do with branchless optimizations? Even very common code that has conditionals can be spectacularly inefficient. So probably everybody has a function like shown on this slide. And under some conditions, code like this can be very inefficient, and with a very simple transformation can be more than twice as fast. Again, here is very common code. Under some realistic conditions, again, it can be optimized to be almost 3 times as fast. And so by the end of the talk, you'll see how these optimizations are done and why they're necessary. What is efficiency in the use of hardware? From the point of view of performance, of course, first of all, you want the optimal algorithm, which gives you the desired result with minimal work. This talk is not about algorithms. After that, the focus is efficient use of hardware. Your computing hardware has computing resources. You want to use all of these resources, or as much as you can, all the time. And the second part is efficient use of your programming language, which is don't do any work that isn't strictly necessary for achieving results. We're going to start with the hardware. So what do we have on the hardware resources that I want you to use all of it and all the time? Modern processors are fairly complex. They have execution units, and quite a lot of them. And that's what ultimately does useful computing. But throughout this talk, we will encounter several of these other blocks, all of which are designed to fundamentally let you use your execution units better. So execution units, what can you do with them? Well, they are the hardware that is used when you have any code that does computing. So here is a simple loop, and it does multiplication and addition. That's what execution units are for. They do addition, multiplication, division, all the computing operations. Now, as you have seen, there is also memory. So overall, the execution picture looks like this. We have the index, loop index. We have the data in memory. The data needs to be brought onto the CPU before it can be operated on. So we load the data from memory into registers, and then we do the multiplication operation on the registers. So that's the computing resources of the CPU, but that's not all the computing resources of the CPU. So I told you to use all of the hardware if you want to get good performance. So what's all of the hardware? Well, it turns out that CPU has, any modern CPU has a lot of compute resources. In particular, it can do multiple operations at the same time because it just physically has multiple computational units. And those are just integer units. It also has floating point units. It has vector units. It has a lot of stuff. So the more complete picture looks like this. We have some data in registers. We can do multiple operations in one cycle, and we get new data still in registers. And how many operations can we do here? Well, a lot. You can try running benchmarks with a loop like this, making it do more and more independent operations. 7 is easy. With adding some floating point stuff, you can do up to 10. If you're careful in what you're doing, even more. Now, unfortunately, it's very rare for a program to achieve the performance of such a synthetic benchmark, and the reason for that is data dependency. So here is a typical example of data dependency. The CPU can certainly do addition, subtraction, and multiplication at the same time. Unfortunately, this program can't do it because it can't do multiplication until it knows the result of addition and subtraction. That's a data dependency. The other kind of dependency is a conditional code where we don't know what code to run until the data becomes available. So these two are very different kinds of dependency. Let's start with data dependency. Data dependency is very common in all programs. Realistically, you never have just independent operations. You always have sequences of operations. So here is our problem. We compute the sum, we compute the difference. We certainly have enough hardware to compute the product, but we have to wait. The way this problem is worked around by CPU designers is with the use of pipelining. What's the pipelining? Pipelining is running multiple streams of instructions at the same time. So this is our sum, this is our difference. It's true that we can't run the product until the next cycle, but what we can do at the same time is run the product from the previous iteration of the loop, I-1. So we can do 3 operations at once. They're just not all from the same sort of moment in time in the computation of this program. So pipelining boils down to running some instructions from the present moment, if you will. If you say I is the present, some instructions from the past, and some instructions are pulled from the future, brought into present. So if you have code like this, where you just have data dependencies, this code is very well pipelined. You compute the first step from the current iteration, the next step from the current iteration, at the same time the first step from the future iteration. So you bring the future computations into the present. Again, if I is now, I plus 1 will be next, but we're doing I plus 1 at the same time as I. And you're not limited to just 2. You can bring in I plus 2 and so on. It's limited by the width of the pipeline, which is just a hardware parameter, how many of these streams hardware can run, and of course, how many compute units you have on the processor. A well-pipelined code, as you can see, it keeps your CPU fully loaded, except at the very beginning and the very end, but let's assume the loop is long, so it's no big deal. So this gives us our efficiency. Use all of the hardware all the time. Now, the difficulty comes in with this workaround if, in addition to not having the data, we solve that problem by pipelining. We also don't know what the future code is. Remember, we're bringing future code into the present, so at the same time as running something for I, we're also running something for I plus 1 and something for I plus 2. Well, that's good if you know what you're going to run for I plus 1. So here is some code that is conditional. You don't know if you're going to execute this or this until you get the result of this comparison. So from the processor point of view, it looks like this. We need to do the comparison. If the result of the comparison is true, we jump to some other place in the code. If the result of the comparison is false, we execute this instruction. And then we skip the next instruction. So that's basically how it looks like. So the problem is you can't pipeline the code because you don't know what the code is until you get the data. Now, in reality, this code actually isn't always hard to pipeline. So if you run this code, it's probably pipelines okay, because there are special conditional instructions in most CPUs. For example, there is on x86, there is a conditional move. x86 assembly is cmove. So cmove copies one of the two of its arguments depending on the condition. This is very different from conditional code. It's always the same instruction. Just what it does depends on the results of the previous instruction. So this code is good to pipeline because we always execute cmove, and it does whatever it does. So if the compiler can implement your conditional code with cmove or some other conditional instruction, you're not going to have pipelining problems. But sooner or later, you're going to run into pipelining problems, even in a code that we said is easy to pipeline. So here is our code that is easy to pipeline, but remember, this sits inside a loop. So we said that it pipelines perfectly like this because at the same time as we're executing iteration I of the loop, we're also executing iteration I plus 1 and iteration I plus 2. Well, that's great, unless I happens to be the last iteration of the loop, and then iteration I plus 2 accesses the arrays past their end, and you can't do it. So actually, there is a conditional code even in this simple loop. So we shouldn't be able to pipeline it. On the other hand, it seems like really a bummer because most of the time, what happens after a current iteration of the loop is the next iteration of the loop. Once per loop, and we're assuming the loop is very long, once per loop, you hit the end of the loop. So do we give up the entire pipelining just because once per loop something happens? Well, we have to handle the end of the loop correctly, but we really don't want to give up the performance. So there is a workaround for this kind of situation, which prevent the pipelining in a situation where usually pipelining works. And the workaround is branch prediction. All CPUs now have them. They had them for a long time. They're basically associative caches. They remember the outcome of the conditional expressions or the branches, which happened in the past in the same place in the code, in the similar circumstances. And what goes into similar circumstances depends on the CPU. They generally remember the call chain and maybe some other state. The assumption here is that if we call this function from this other function and the condition was true, and we did it again and the condition was true, it's probably going to be true the third time, and so on. CPU actually makes that assumption and proceeds to pipeline the code as if this assumption was true. This is called speculative evaluation. Now, the catch here is that the speculative evaluation precedes the actual evaluation of the condition. So we go ahead, pipeline the future code, bring it into the present, make a guess about it and bring it into the present, but we don't actually know if the condition is true or not. And we won't know for several cycles. Conditional instructions are fairly long, take some time to evaluate them. at the point where we find out if our prediction was correct, well, if it was correct, we're good. We evaluated the right instructions, we just proceed forward as if this condition didn't even exist. What happens if we guessed wrong? Several things need to happen. First of all of the computations that we predicted and were wrong about have to be discarded. That's called pipeline flush. We loaded our pipeline with the future instructions. Well, they're all wrong. We obviously have to start the new correct computations. That's okay. The bigger problem is that the computations we mispredicted may have results. And all of these results have to be undone like they never happened. Well, what about things that cannot be undone? For example, if we wrote something into memory, the old content of the memory is gone. There's no way to undo it. Memory has no backup. What about something more dramatic? Maybe we accessed the array past the end of the array and we crashed. How can you undo if you already crashed? Anything that you cannot undo, you cannot do speculatively. You have to wait. In particular, so here is a very common example. Let's say, so we check for pointer, and if it's not null, we use it. Very common in programming. Let's say that pointer is almost never null. Well, this write cannot be executed speculatively because we can't write into the 0th address. So this write and the associated error, if p happens to be null, have to be held in some special buffer, and the CPUs now have them. Any CPU that has speculative evaluation has to have some kind of storage to hold things like memory writes and potential errors until it knows if these irreversible changes become real or not. So x86 has an array of memory buffers that are the write buffers, they're called. They're used precisely for this. They are holding the speculative writes until we know if speculative becomes real or not. So let's go back to our loop, which we said is a well-pipelined code. Well, we were correct. It is well-pipelined code. We just didn't know why we were correct. In reality, we're correct because the branch is predicted. And the prediction is there will be the next iteration of the loop. At the end of every loop, there is a branch misprediction once. So that branch misprediction happens. Pipeline gets flushed at the end of every loop, but it's once per the entire loop. If the loop is long enough, it's well worth it because we get a lot of pipelining and only one flash. So now let's look at how this code looks like from the point of view of the CPU. So from the point of view of the programmer, it looks like this. We wrote a loop. From the point of view of the CPU, it doesn't look like this because the CPU doesn't actually evaluate this condition between every line of the loop. The CPU computes the first line, the second line, the third line, and yeah, somewhere in here in parallel, it evaluates the condition. But CPU just proceeds with all the lines of the loop as if they were unrolled. And then it pipelines this code. This is hardware loop unrolling. It's different from the compiler loop unrolling. So on the compiler, loop doesn't get unrolled. Compiler still generates the loop. The processor generates the unrolled code. So let's see now how that looks like from the point of view of the processor. Well, here is some hard to pipeline code where we don't know if we're going to be doing plus or star, depending on some data here. So what does it look like from the point of view of the CPU? Well, it looks like this. We check the condition, and then we either do this or we do this. What branch predictor does is it makes a guess and it just removes these jumps basically from what it thinks will be the predicted sequence. So, and then it pipelines it. So if it thinks it will be true, it just does this instruction and then immediately goes and does this instruction and pipelines it. Okay, let's see how it actually works in the code. So here is some loop. And what it executes depends on this condition. We're going to treat it as a Boolean, so some array here. And what we're going to do is compare what happens if the condition is predictable versus condition is not predictable. And predictable, we can make it all 0 or all 1. And not predictable, it's some kind of random values or zeros and random zeros and ones. If it's predictable, we expect to see this. So this if true part will be guessed. The false branch, CPU will ignore, it won't happen. And instead of this conditional code, we're going to see this non-conditional code, including a non-conditional jump. That's what CPU is going to evaluate speculatively. And then at some point later, there may be pipeline flush. Okay, we're now going into the demo part of the talk. For this part, I'm going to use the following tools. And if you want to reproduce this at your leisure, you have to get the same tools. I'll use Google Benchmark Library. There are several other benchmarking libraries available. They all work more or less the same, but this is the one I'll be using. I also will use perf, which is a Linux profiler. And again, you can use vTune or some other profiler that gives you access to the hardware performance counters, but this is the one I'll use in the demos. Okay, let's see the first demo. And the first demo will be exactly what we were talking about. So ignore the entire Google Benchmark framework. You have to read the documentation and learn how to use it. Focus on this part here. This is the code that we're going to measure. So I'll only be talking about the code that we're going to measure. Ignore what happens before and after, doesn't matter for this presentation. This is our loop. This is our condition. And we execute either this or this. How predictable is our condition? Okay, I pulled the pointers out of the vectors just so I don't have to deal with any possible STL stuff. In reality, it doesn't matter. Vector optimizes away, but I just want to be sure, that I'm not measuring any vector performance. Okay, so how predictable is our condition? Well, this is actually our condition. And why didn't I just say 0? I didn't say 0 because the compiler tries really hard to figure out which computations it doesn't have to do. If I put 0 here, some optimizing compilers will figure out that this is always 0. I don't know of any compiler that knows that rand returns positive numbers. So this seems like it should be random, but it's not. It's always true. So this is entirely predictable. On the other hand, this is exact same code with one change. This is unpredictable. Rand is not a very good generator, but good enough for our purposes. Roughly half of them will be true, half of them will be false, and this is not something that the compiler or the hardware can predict. So let's run the benchmark. This is the predictable one. It can do 600 million loop evaluations per second. And this is the not predictable one. Same code, it can do only 160 million loop evaluations per second. Now, we started from writing code, so we know the reason. The reason is the predictor failed, the pipelines got flushed all the time, and that's why it runs so slow. But let's say you didn't know that upfront, you start from the program which does whatever it does, and you want to know why it's so slow. That's where you need profiler. So again, I posted a link to the documentation of the profiler, but we can get cumulative stats for the entire program with this perf profiler. So here they are for the predictable branch. And you see 0.5% of all branches were mispredicted. Branch misses, that's the mispredictions. And we were doing 1.4 instructions per cycle on average. Same thing with our mispredicted program. Over 9% of all branches were mispredicted, and we were doing only 0.7 instructions per cycle on average, half as fast. So I have demonstrated to you that indeed branch predictions matter, and predictable branch evaluates much faster than non-predicted branch, at least if there was pipelining to do. Branch misprediction is really expensive. On a good program, you will see less than 0.1% branch misses. 10% is very bad. It's really slow. You rarely see more than 10%. So if you see anywhere like 5%, 2%, it doesn't seem like much, but trust me, it's a lot. On the other hand, optimizations that are designed to improve this metric and eliminate branch mispredictions are usually difficult, invasive, complex, hard to do, may cost you more memory. And on the other hand, branch predictors themselves are actually pretty complex. They remember quite a lot of things. So it's not as simple as, okay, if it's always 0, it's predicted. If it's always 1, it's predicted. If it's not predicted. They are more smart than that. So because the optimizations are so difficult and the branch predictors themselves are pretty smart, you never know what they're going to do. Don't do this optimization prematurely. Always measure by a profiler, but if the profiler tells you that you have several % of branch misprediction, now it's time to do what I'm about to show you how to do. Okay, just to drive this point home, here is a branch that is 50% ones, 50% zeros, but it's not really random. It's 0, 1, 0, 1, 0, 1. You would think that it's not predictable. But it actually runs pretty fast. It runs much faster than truly non-predictable branch. And the misprediction rate isn't that bad. So branch predictor detected the pattern, the regular pattern, 0, 1, 0, 1, 0, 1, and predicted the branch based on that. If you didn't expect that and you spent time optimizing that code, you probably made it slower. So don't do this optimization until you know that it needs to be done, and the only way to know is by measurement. Now, let's say you have measurements that show high rate of branch mispredictions. What do you do? Well, first of all, you look at what's actually on the branch. And you have to look very careful, because what you think about as the branch isn't necessarily what the processor thinks as the branch. Here is a code with a condition. And what a programmer thinks, what does the programmer think? Programmer thinks, if we always end up here, then it's a predictable branch. If we always end up here, then it's a predictable branch. And if we don't know, then it's not a predictable branch. But that's not how the processor views it. The processor views it like this. If X is always true, it's a predictable branch. If X is always false, but y is always true, it's a predictable branch. If sometimes x is true and sometimes y is true, it's not a predictable branch. Why such a difference? Well, because this operation, the logical OR, is short-circuited. That's true in C, that's true in C++. The evaluation must stop. It's not an optimization, it's required. The evaluation must stop as soon as the result becomes known. So if x is true, no matter what y is, the result is true, so y should not even be evaluated. This is actually important. It's what let you write code like this. If star A is true, B may be null here, for example, and that's perfectly correct. This will never crash. So that's what lets you write code like if P and star P. So this is fine, but from the performance point of view, it may end up being very expensive if you always get the same result, but you get there by different ways. Here we have conditional code. Again, look only at the benchmarking loop. Conditional code, B1 or B2. What do we know about B1 or B2? Well, B comes from C. Okay, the first term is entirely random. The second term is always the opposite of it. It's also entirely random. But altogether, it's perfectly predictable. One of them is always 1, and the other one is always 0. So this is a perfectly predictable branch. We always evaluate the true branch. We never go here. Except it's not predictable at all. The hardware says not predictable. Why? Well, because from the hardware point of view, it's 2 branches. It's if this, and then only if it's false, then if this, and both of them are random. The predictor may have caught on the pattern that if this is true, this is false, but at least the first half of it is unpredictable. Okay, if you are in this position, so if the profiler shows that you have high rate of misprediction, and at the same time you know that it's almost always true, what do? You may be tempted to use a temporary variable. Don't do it. First of all, compiler's bread and butter is getting rid of temporary variables. It'll remove it for you. Second, it's still 2 branches. In the root of the problem is Boolean logical arithmetic. So you have to get rid of the Boolean arithmetic. Integer arithmetic works in this case because Boolean values are equivalent to 0 and 1. So plus is equivalent to or multiply is equivalent to and. You will get here 0 only if they're both 0. Bitwise arithmetic, bitwise integer arithmetic works, and it's not short-circuited. For more complex expressions, you have to be careful to find correct alternative forms. It's always possible, but you have to think about it. There is another catch here, is that some compilers will look at this and convert it to this. They're doing it as a favor to you as an optimization, except in this case, it's not a favor to you. It's more likely to happen with plus for some reason than with or. That's just how the optimizers work at the moment. May change in the future. If you make this optimization, you have to run the profiler. So the optimization would look like this. The only difference is instead of or, I put the plus here. And then I would run it with a benchmark. And then I would run it with the profiler. And yeah, it's much better predicted. Also, it's much faster. In the number of branches per second and in the number of instructions per second. 0.74 instructions per second, 1.3 instructions per second. Per cycle, sorry, per cycle. And fewer mispredictions. So in this case, it worked. If the profiler showed me that it didn't work, I would have to look at the assembly output and figure out that the compiler fights me on this. And then I would have to use some other instruction, like maybe bitwise OR. Note the general trend about this kind of optimizations. Any optimization of branches almost always results in doing more work. So if you write x plus y, it always evaluates x and y and the sum. If you write x or y, it always evaluates x, sometimes evaluates y, and it wouldn't evaluate the or if x was true. So Boolean expressions are less work. The branchless expressions, we removed one branch here. So there were two branches. We cut it down to one branch, so it's fewer branches. Always more work. The reason it's an optimization, and it's an effective optimization, is because remember that CPU has a lot of compute units. And while I told you that your goal is to use all of them all the time, realistically, you're not going to be able to do it. Except for very special programs, CPU always has some compute resources idle. And because of this, it can handle a bit of extra work. On the other hand, branch misprediction is very expensive. So you're trading some extra work that probably happens at the same time as the other useful work, so it doesn't really add any time. You're trading that against a very expensive pipeline flush. But on the other hand, there may be a lot of extra work. If your expressions are complex, if it's not just x or y, you may be having some very complex expressions that are difficult to evaluate, and then you have to measure again. You can't predict this. Okay, let me show you what the branchless optimization taken to the extreme. I'm going to eliminate branches completely from a conditional piece of code. So here is my conditional piece of code. And the idea of branchless optimization is to use Booleans as integers. They're convertible to integers. They're 0 and 1. So instead of this code, I'm going to have this code. I'll evaluate both of my expressions. Again, remember, extra work. I'll put them in an array. I'll read the correct element of this array and add it to my result. There are no conditionals here. This is a stream of instructions that is entirely predictable from start to finish. Unlike this, where your instruction varies depending on the condition. So there is, this code has jumps, this code has no jumps. Will this code be faster? Well, that depends. First of all, if the branch is very well predicted, then no. Predicted branches are cheap. If the branch was frequently mispredicted, then it depends on what's the cost of actually computing both of these expressions. If the extra computations are small, you may even get them for free. Remember, CPU has idle hardware most of the time. Let's see an example. Here is our conditional code. If true, I'll do this. If false, I'll do this. The branch is entirely not predictable. Here is my branchless transformation. I'll evaluate both of these expressions always, unconditionally. I'll store them in arrays. And in this case, because I wasn't adding them to the same sum, I was adding to different sums, I have to have two arrays. And I'll always add something to both sums, but I'll be adding zeros half the time. Definitely a lot more work. I'm always computing both minus and multiply, and I'm adding zeros. Let's see what's faster. Branchless is faster. With all the extra work, it's more than twice as fast. If the branches were predictable, it wouldn't be the same at all. But the branches are not predictable. Extra work isn't too much. Branchless is faster. Again, I want to caution you here because sometimes the compilers will do this transformation for you. What we had on the previous slide is essentially a conditional move coded in C++. This always moves, this always adds, but what it adds depends on the value of condition. Sometimes the compiler will replace conditional code with instructions that basically do the same thing, and the compiler usually does it more efficiently than you can. Because it does it at the machine code level, you have to cobble it together at the C++ source level. The compiler will usually do a better job. In particular, you almost never want to optimize this line. The compiler will almost certainly do the conditional move here. So never optimize this code because it looks conditional. Always wait for the profiler results. On the other hand, always do use the profiler, because your code may look very similar to this, and the compiler may not recognize it. Again, let me show you the example. Here is our loop, and in this loop we call a function, f. And here is the function, condition, boolean, term, sum, and this is what it does. Well, this is very similar to a conditional return, only instead of returning it, we're adding it to the argument. Could compiler optimize it? Yeah, in theory it could. For some reason it doesn't. How do we optimize it if we want to? Well, we optimize it like this. We wanted to say, if it's true, add x to s. Well, this is the same thing. If it's false, it's just 0. So the result is the same, but it always multiplies and it always adds. And half the time it'll be adding zeros. What's faster? Branchless is faster. More than 2 times faster. But again, remember, you don't start with this branchless optimization. What you start with is this. You run the profiler, and the profiler says, very high rate of branch mispredictions. Okay, now you go do the branchless optimization. So as I showed you on many examples, you always need to use the profiler. What I'm giving you here are sort of typical examples of where it works, the optimization, where you do it, and where you don't do it. Here is another case where you don't do it. Conditional function call. You can convert it to branchless code. This is branchless. Well, at least it's free of conditions. This almost never works. If you have high branch misprediction, you can try it. It almost never works. Why? Well, first of all, if the functions were inlined, this is going to kill your performance completely. Indirect function call through a function pointer, really, really bad compared to inline functions. But even if it wasn't inlined, a function call acts almost like a branch in the sense that there is a pipeline flush. The compiler typically doesn't know which instruction is going to be executed next. Sometimes it can predict it, and then it might work. Measure. So this needs to be confirmed by measurements. Probably won't work. So at the end of the talk, let's recap sort of our train of thoughts. We want to get the best performance from our programs. For the best performance, we want to use the hardware as efficiently as possible, which means not letting any hardware sit idle. Processors can do many computations at once, every cycle, and we want to use all of that. Why can't we use all of that? Typically, we don't have enough data to do so many computations at once, because we need the result of the previous computation to run the next computation. There is a workaround for that. It's called pipelining. We take the previous data and we use it for the next operation from that data stream. And at the same time, we take the next data element and do the first operation on that data element and the next data element and so on. So we're running instructions from the past, present, and future at the same time. This works great until we hit conditional code, where we don't know what the instructions from the future are, where the next instructions themselves are data dependent. There is a workaround for that too. And that workaround is branch prediction. The CPU guesses what the next instruction will be and proceeds forward. If the guess is correct, everything is well. If the guess is incorrect, it's pretty bad from the point of view of performance. So what's the workaround for that? Well, where previously everything was handled for us, now it's up to us, the programmers. Now we have to come up with a workaround for that, and that is branchless programming. You use fewer, all the way down to 0, branches. And I have shown you the techniques for that. Remember, these optimizations are tricky. They could make your code much faster. They could make it slower. You don't do them in advance. You always use the profiler to detect where they need to be done and also to confirm that they worked. And if the compiler decides to help you with a branchless optimization, don't fight it for it. Compiler is better at it than you are. But if the compiler doesn't do it, then use the techniques I have shown you, validate them with measurements, and make your code run faster.